everyone, I am Meghna Indlamudi. I chose the paper titled Kernel Logistic Regression Approximation of an Understandable ReLU Neural Network. As we all know, interpretable models in medical applications play a crucial role in ensuring the trust, adoption, and ethical development of machine learning technologies. In healthcare, decisions made by predictive models often have direct consequences on patients' well being, making it imperative for these models to be understandable and interpretable. In cases where models need to comply with medical ethics and standards, interpretability becomes a fundamental requirement. Hence, the need for interpretable models in medical applications is not just a technical consideration, but a fundamental requirement for ethical, transparent, and trustworthy implementation in the healthcare domain. Therefore, here comes the main objective of our project, of our paper. Basically, the problem addressed in this paper is to introduce an innovative approach in developing an interpretable neural network model for medical applications, focusing on cardiovascular event prediction using the Framingham dataset. Now, we delve into the Saturn model, a cool new way of making sense of complex data. It is an interpretable neural network model that combines the advantages of multivariate adaptive regression splines, generalized additive models, neural additive models, and neural networks. Saturn is just like a car with a special engine. Its core function, which uses a combination of simple curve like functions called univariate spline functions. Interestingly, this engine is so powerful that it's equivalent to logistic regression but with extra twists. When we train Saturn, we aim to find the best setting by balancing between correct predictions and keeping things simple. The beauty of Saturn is that it not only trains well, but it also does so in a way that's easy to understand. Even with a sigmoid output layer, Saturn can be linearized with respect to its parameters with lot of hidden units, and we can still train it without making things overly complicated, enabling through solving a convex optimization problem. Here we have taken Gaussian and circle datasets, and the below graphs here shows the estimated decision rule in red and the partition boundaries in black. And the table shows the summary of comparison on both datasets with average accuracies obtained on test and train data. And the blue rows here refers to new approaches used in this paper, the Saturn, kernel logistic regression, and EKLR. We can observe that for Gaussian dataset, kernel logistic regression records accuracy of 81% or 80%, whereas Saturn does it to 90% in our circle dataset. These are the results for our original dataset, which is the Framingham dataset. Saturn produces similar or even higher accuracies than the other methods. The Saturn, composed of 40 neurons, reaches 72% of area under the curve on the validation sample, whereas the GAM gives 69% and NAM gives 70%. The greedy methods such as RF, Mars, and GAM, they tend to overfit basically. In comparison with the nonlinear models, the proposed model is basically compared with various nonlinear models, and it demonstrates competitive performance. It is shown to achieve similar or better predictive performances than other nonlinear models such as the random forest, Mars, or GAMS and ReLU neural networks. The paper also introduces the use of kernel logistic regression and the expected kernel logistic regression, which is EKLR, as approximation methods for Saturn. The approximation methods are calculated using formulas and predicted for Saturn using the Saturn things. The results indicate that these approximation methods are not only faster but also achieve similar or even better predictive performance compared to neural networks and other nonlinear models. As we increase the number of hidden neurons, we observe that the approximation error between Saturn and the kernel logistic regression tends to stabilize. This suggests that our model becomes more robust, indicating a consistent and reliable performance in approximating the desired outcomes. Here are the experimental results obtained. In our study, usually the experiments are conducted using both simulated and real data sets to confirm that the proposed approach is effective. Unlike previous methods, our approach Saturn usually outperforms others in terms of making accurate predictions and being scalable. Saturn is tested on various datasets, including the Framingham dataset, and found it to be better than other nonlinear models. Importantly, it also made sure our model is predictable, meaning we can understand and explain its decisions. It is done by visualizing how the model breaks down features and estimates curves, giving us insights into how each input variables contributes to the final classification decision. To conclude, the paper introduces a user-friendly neural network structure using ReLU activation function, which is built on a sum of univariate spline functions. It is demonstrated that as the number of hidden neurons increases, the network behaves like a kernel logistic regression with a unique kernel. The end result is an additive model made up of individual functions tied to training data, ensuring guaranteed convergence and a distinct spline decomposition. Thank you.